This demo will review OpenShift Virtualization, a way to bring virtual machines into your OpenShift cluster and connect them into other pod-based, Kubernetes-based applications running inside of there. So the interesting part here is that OpenShift Virtualization puts virtual machines into pods, so we're going to be able to look and see and touch all of those different components inside of there and connect them in with all of the other OpenShift features and capabilities. So as with any virtualization solution, there's a couple of precursors that we need before we can begin. So quite simply, these are compute, storage, and a network. And they're pretty straightforward to use and configure inside of our OpenShift deployment. So when we look at our cluster here, we can see that I'm running OpenShift version 4.4.10. At the time of this recording, that is the most current version. And in order to deploy OpenShift Virtualization, we need to deploy the operator. Now, in my case, I've already done this because it does take a couple of minutes when you do it, and we don't want to sit here and watch pods churn. So what we see here is the container native virtualization operator. So be aware that the name of OpenShift Virtualization has changed a little bit over time. So it is currently publicly known as OpenShift Virtualization. Previously, it was container native virtualization. Prior to that, it was a part of the Kubernetes native infrastructure project. So sometimes you'll also see, for example, out here in the deployment name, references to the hyperconverged operator, or HCO, that are a part of that naming scheme. So if I look at my container native virtualization operator deployment here, we can see all of the standard things associated with an operator deployment. In my instance, I am using version 2.3 for this particular demo. Note that the OpenShift Virtualization and OpenShift versions, while they are not the same, they are tied together. So OpenShift version 4.4 and OpenShift Virtualization version 2.3 are a pair. OpenShift version 4.3 and OpenShift Virtualization version 2.2 are a pair, and that will continue going forward. So once the operator is deployed, I need to, of course, instantiate it. In this instance, we have our KubeVirt hyperconverged. We go in and if I were to create a new one, all I'm doing is creating a new instance of this object and allowing it to deploy into our OpenShift CNV project. So notice I'm already in the OpenShift CNV project. If I were to come in here and look at all of my pods, we can see all of the things that make up our OpenShift virtualization. So for example, here is the containerized containerized data importer pods running. We see things like here's the KubeVirt node labeler, which is what looks at and ensures that the nodes have, for example, KVM enabled and accessible on them. So that way we won't schedule a virtual machine to a node that cannot host a virtual machine. We see the nm state operators pods running inside of here. This is how we configure our node networking using Network Manager and the nm state operator. As we move down, we see a couple of other things. So here's Virt operator. This is the actual controller Virt controller is the actual controller that's implementing our API. Virt operator and Virt handler are used to control the virtual machines that have been deployed across our cluster and across our nodes. Okay, so compute, pretty straightforward. We just looked at that. We're using the nodes in our cluster. If I were to look at my nodes, we can see this cluster has 3 control plane nodes and 2 worker nodes. So those nodes do need to be physical nodes that have access to KVM. So if you have virtualization extensions on your processor, whether it's AMD or Intel, make sure those are turned on. Now, you can technically use nested virtualization as well as emulation. Neither one of those is supported, but you can use it, for example, in a lab or in a test environment. Just be aware of performance penalties associated with each one of those methods, as well as, of course, the lack of support. So, compute taken care of. Let's take a look at networking. So, networking, as you would expect, we need to be able to connect our pods to the outside world. And in this case, I'm going to use a secondary interface on my worker nodes in order to do this. So we can't see it through this particular, through the GUI here. So what I'm going to do is connect to and use the CLI. So from the CLI, what I want to do is look at a couple of different objects. The first one is the current node configuration. And if I look at the NNS, I can see that one exists for each one of the nodes. And if I look at the details for one of these, by doing an output to YAML, I can see precisely what my node configuration looks like. So first, NNS way up here at the top is node network state. And as I look down through the status YAML, we can see the definition for each one of our interfaces. So for example, here I have a bridge interface. Let's scroll down a little bit. A bridge interface named BR1. It has one port connected to it, ENS4, no spanning tree enabled, and no IPv4 or IPv6 address assigned to this particular interface. So this is that second interface that I was describing a moment ago. So it is connected to the 192.168.14.0/24 network. So when I use this in a few moments, this is where we're going to expect to see our virtual machines receive a DHCP address from. Now the other interface on my particular nodes is ENS3, and ENS3 is connected directly to the lab network. In this case, it is a 10.0.101.0/24 network. And we see here ENS3 is directly connected to that. So my nodes have two interfaces. One is connected to the public management kind of SDN overlay, right? This is the network that OpenShift uses for basically everything. The other interface is connected directly to the external public world, a different network. Now, I could, if I wanted to, use the network state operator, the NM state operator, in order to do things like configure bonds, put VLAN interfaces on top of that, set up bridges for those, right? I can configure this just like I do any other node, leveraging the network manager concept. And if I were to connect to my node, I would be able to go and look at and see what that actually looks like. However, I want to do this the Kubernetes way. I want to do this using NM state operator instead of having to connect to and modify the node on every boot using ignition or maybe using the machine config operator. So we do that using a node network configuration policy. So we see here I have one creatively named worker. So this one will apply to all workers to create BR1 using ENS4. If I look at this guy, again, doing an output to YAML, we can see my desired configuration. So first and foremost, what we have here is a node selector. So for all worker nodes, I want you to create a new bridge interface using port ENS4 with no IP address assigned, and give it the name BR1. So pretty straightforward. Once we create that object in the cluster, we can see whether or not it gets applied using the node network configuration enactment in NCE. And we can see here, by looking at the NNCE, a couple of bits of information. So first we have the name of the node, followed by the NNCP that we are looking at. And we can see here with our control plane nodes that the node selector doesn't match, but down here with our worker nodes, it has been successfully configured. And I can take a look at the details for one of these, again by doing an output to YAML. And I can see the desired state and what we want it to look like, and then up here we can see the different conditions as it went through and applied our configuration. So it went from progressing to successfully configured relatively quickly. It only takes a few seconds for it to apply our configuration here. So with that done, we have now configured the node networking. Now we need to enable our pods to connect to that particular network. And this is done using a network attachment definition. So this is independent of OpenShift Virtualization and the NM state operator. This is how we tell or inform Kubernetes, inform OpenShift, that a pod can connect to whatever Multus network I want to connect it to. So if I look at my network attachment definitions, we can see that I have created one named CNV-BR1. And as you would expect here, this is a standard CNI definition. When I look at this, we see I'm using a plugin type CNV bridge, which bridge I'm pointing at, BR1, and then it is of type tuning. So these are specific to OpenShift virtualization, but this network attachment definition, the concept, the application of these is not. It is a Kubernetes Multis concept that can be applied to any other node network or other SDN that happens to be inside of our cluster. Okay, so we have now looked at our compute, we've looked at our network, so let's look at storage. So inside of my cluster, I have a single storage class. We can see it is creatively named Managed NFS Storage, and it is the default storage class. So the reason why I'm using NFS in this case is because I want read-write many storage to be available to my virtual machines. This is for live migration. I can use read-write once, RWO PVs. However, I cannot do live migrations when I'm using those. I need to use RWX in order to do live migration. So how do I tell, in particular, the containerized data importer, which is going to create PVCs on my behalf when I instantiate VMs, the defaults for my storage classes? Because it will, if no configuration is provided, it will assume all storage is read-write once. In order to do that, we want to look at our storage class defaults for OpenShift virtualization. So we have a configuration map inside of the OpenShift CNV namespace. This was where we deployed the operator to, that contains that configuration information. And in particular, when we look at the data inside of there, we see a bunch of different options available here at the top. So first, you'll notice that there is a couple of things in common: local SC, managed NFS storage. This is the name of my storage class, as well as this access mode and volume mode. So what happens here is when containerized data importer is requested, when the data volume paradigm, rather, not just containerized data importer, when the data volume paradigm sees that a new PVC has been requested of a particular storage class, it will check here and use the access mode and volume mode that's provided, or it will use the default if none is specified for that storage class. So what this means is that when I create a VM using this storage class, it will default to read-write many. Therefore, I can do live migration. So important that you configure this if you are not, especially if you are not using block storage, but also kind of anytime you want to change these from file system to maybe raw block or whatever that happens to be for your virtual machines and the storage class you happen to be using. So note that OpenShift Container Storage does have the ability to do read-write many with block storage devices. So that would definitely be one that you want to tune and adjust based on what your needs happen to be and how you're using that storage option. So with that taken care of, we now have all three of the core, the legs of that stool, so to speak, to be able to begin deploying virtual machines to our cluster. So if I come up here to workloads, you'll notice that we have, after we deployed our operator, we have GUI integration directly with the OpenShift console. So this comes not only through this virtual machines menu item and the ability to create and manage them through this specific interface, but also things like on the overview. If I look at the overview, you see that I have virtualization status at a high level here, down here. Underneath the cluster inventory, you can see the number of VMs that I have deployed. Right, there's a lot of information, a lot of other little ways that it integrates throughout the user interface. So let's go to our virtual machines and let's switch to our default project because that's where we have created our network attachment definition. Note that those are namespaced. So let's go ahead and create a virtual machine using the wizard. So the first thing when creating a new virtual machine is we want to specify where it's going to get the operating system for this virtual machine. And there's 4 different options that we have available here. The first one is PXE. Quite simply, it will PXE boot the virtual machine. This is the only option that is diskless. So I do not have to provide a PVC for this if I don't want to. Do note, however, that OpenShift Virtualization does not provide any of the PXE infrastructure. Essentially, you're connecting it to an external PXE-capable network, so you provide DHCP, TFTP, all of the other things that are needed there. The second one is URL. So this will use the containerized data importer to reach out to that URL and pull in that QCOW or raw disk image from an HTTP, HTTPS, S3 endpoint and put it into the PVC that will be used for our virtual machine's disk. Container is to pull a container image in and use that for our disk. So the difference between that here is URL will pull that disk image in and put it into a PVC. Container will pull that as a standard container image from a registry. When I instantiate the VM, when I turn it on, it's going to treat it just like any other container image. It will create a copy on write layer on top of that. Any modifications, read, writes, etc., or writes, changes, etc., that the virtual machine does are happening in that copy on write layer. When that virtual machine is terminated, so when it's powered off or if it is migrated, that copy on write layer is removed. So this is helpful. This can be useful if you have, for example, a template virtual machine and you want to attach additional PVCs to act as application persistence. So I can pull in that virtual machine container image, power up or instantiate based off of that, and then attach other PVCs for application data. Last but not least is disk. So disk is basically just telling it, hey, use this existing PVC. You don't need to do anything like with URL, which will use containerized data importer to bring in that disk image. So I am going to use URL. I happen to have a locally hosted version or a locally hosted instance of the RHEL 8.1 KVM image. So all I did here was go to access.redhat.com, go to the download page for RHEL 8.1 and pull down the KVM image. I've made no modifications to it whatsoever. It's just that standard image. I can use RHEL, I can use Fedora, I can use pretty much any cloud image that I have prepared here. Just keep in mind, and there's a KCS article that has the supported guest operating systems. So you could do the same thing with Windows if you wanted. You could create your own template image using that. So I need to tell it which operating system I want to use. In this case, come on. In this case, I'm going to use, if I can get it to cooperate, I'm going to use Red Hat Enterprise Linux 8.1. So the flavor here, this is how I specify my RAM and CPU. So custom, of course, I can provide that myself, or I can use the t-shirt flavoring that I have available here. So small, for example, represents 1 CPU and 2 gigabytes of RAM. So I'm going to go ahead and pre-select that. Workload profile applies some settings to lib, virt, and qemu when we instantiate a virtual machine. So if you've used Rev before, these should be a familiar concept. So for example, if I use high performance, it's going to do things like automatically turn on I/O threads, automatically enable CPU and NUMA pinning, a number of other things in there to give that virtual machine maximum performance at the cost of some additional resources. So my virtual machine here, I'm just going to go with desktop workload profile because it's a lab and it's a temporary VM just for this demo. And I'm going to give it the ultra creative name of RHEL. So the next step is to specify our networking. We can see by default, it will use a virtio NIC type connected to the standard pod networking on our host. Now note this is masquerade, so it's basically NAT in from the outside world. I don't want this. I want to use our bridge that we talked about earlier. Note that I can specify a MAC address if I so choose. Moving on, I can specify storage. So in this instance, I am going to change this to use a 20 gigabyte drive. See, I still have my URL for my QCOW2 up here. And I don't need to because it's the default storage class, but I'm going to anyways. I'm going to specify my managed NFS storage here. Now I can add more disks if I so choose. I have the same option with network adapters, so I could have as many network adapters as is supported by the underlying VM hardware type, the default being Q35. I do want to use Cloud Init for this particular virtual machine. This is so that I can log in on the command line. So I'm going to provide the world's simplest Cloud Init here, which just sets a password and allows me to log in. If I wanted to attach a CD-ROM, maybe I'm trying to load the operating system that way, I can do that from this interface. And then last but not least, do a quick review of all of the decisions we just made before defining our virtual machine, creating the virtual machine. So if I go to my list here, we can see that I created the virtual machine named rel. Its status is currently importing. So our virtual machine definition exists here. And if I were to look at the YAML, you can see all of the metadata that are associated with our VM. So you see the CPU and how many CPUs are associated with it. It is one core on one socket with one thread. I could have, for example, multiple cores on multiple sockets or multiple cores on one socket, whatever configuration works best for my application. We can see our disk definitions. As we scroll down, we see our memory definition is here. See, here's our Q35 machine type definition. Our Multis network definition happens to be here, so we can see NIC0 is connected to CNVBR1. So this is a standard Kubernetes YAML object definition. This follows the same pattern as any other Kubernetes object that we happen to be interacting with. And importantly, I can copy this directly out and I can use it as a template to create additional virtual machines in the future. So I would just need to change the virtual machine name in order for that to happen when I'm creating from the command line. Now, why is this important? This is important because, well, maybe I need to spin up, 2 or 5 or 10 or 100 virtual machines very quickly. And I'm going to rely on OpenShift Virtualization to import those according to this data volume template definition. So we see here, I'm going to create a read-write mini. So every time I submit this, it's going to create a read-write mini PVC that's 20 gigabytes in size using the managed NFS storage class, and it's going to pull in this disk image. So if we look at our pods, so first remember our virtual machine here is in a status of importing. And if we look at our pods, we can see that we have an importer pod that's running. We also have, if we were to look at our persistent volume claims, we see our rel root disk, which is bound to this particular PVC, which is a read-write mini PVC. So when I created that VM, it put in the PVC. The PVC was bound to a PV that was dynamically created by our storage class. And then our importer pod, because we're using a data volume, was instantiated with that PVC attached. And if I look at my importer pod here, and in particular if I look at the logs, we can see that it is pulling down that image from my HTTP server. So it's pulling that in, it is putting it onto the PVC that has been assigned. You can see it's about 80% done. This is about a gigabyte image and I'm on gigabit network, so it'll take it just a little bit to finish up. But if we were to look at the events here, we can see exactly what I just described. So you can see it's waiting on the volume to be bound. So we have a couple of errors about the PVC basically has not had a PV bound to it yet. It was assigned to the node, it was started, and then we begin to do the import process that's happening here. And you can see it's almost done. So we'll give that just a second. And after it is done pulling the image down, what we're going to see is it's going to expand the disk for us as well. Before the pod terminates, you can see it is now not found. So looking at our virtual machine definition now, you can see that the status is off. It is no longer in importing. If I were to come into this virtual machine definition, there's a couple of things that we want to do. So first, you see I can modify network configuration here. I can modify disk configuration from here. Note that we do have a cloud init disk because I did specify a cloud init inside of my configuration. We can also do things like attach secrets. We can attach config maps, right? There's a number of different things that we can use to pass information into our virtual machine using volumes. But at this point, I'm going to turn on our virtual machine. So the first thing you'll notice, it was scheduled to worker 1 here. We see it's in the starting status, and now it is running. So I can switch over and look at our console and see it going through the boot up process. Now, the virtual machine interface here abstracts away much of the details that are happening underneath, but I can very easily look at the pods here and see my virt launcher pod for my rel VM. And if I look at the details associated with this, it is just like any other pod that's running in my environment. I can look at the logs associated with all the things going on inside of here. I can look at the terminal. And importantly, see we have our compute container inside of here. If I were to do a ps-ef, I can see the processes that are associated with my virtual machine. So you see here I have QEMU KVM, which is our actual virtual machine process. I would expect to see at least one of these processes for each CPU, each core that is assigned to our virtual machine. And then Virt Launcher, which is doing our virtual machine management. So it's doing things like if the resources change, if a property changes, Virt Launcher is what informs QEMU KVM that something has changed. And if we switch back over to our virtual machine, which should be done booting by now, we see that we have our console. So I will log in using the password that I specified in my Cloud Init. And if I do a quick check of our IP address, you can see that it has been assigned the IP of 14.198. So just to quickly show that we have external connectivity, I can do a ping against that IP address and see that it comes up and is immediately pingable, just as we would expect. From here, I can also ping out to the world. So we are able to reach out to the internet as well. Now, because this is a bridge network to the public interface, this means that this pod this virtual machine would have to traverse the standard egress into our the remainder of our OpenShift cluster. Now, if I used a pod network, right, with the masquerade or the bridge configuration, if I used a pod network, then I would be traversing OpenShift SDN. So we'll be able to do things like assign a service to it and be able to access through that service name. Because this is connected to an external world, just like any other virtual machine that's connected to a layer 2 network, it's following a more traditional network path in and out of other OpenShift services inside of the cluster. So while we're here, let's take a look at a couple of things. So first, in the overview screen, we can see things like CPU, memory, a lot of other details inside of here. Note that because this is RHEL 8.1, or RHEL 8, it does have the QEMU guest tools already installed, so it's surfacing up information like the IP address by default. I can see different properties about my virtual machine. Now, these will take a little bit of time to populate. That's why we're not seeing them here yet, but it will eventually get there. I can also, from my actions menu here, I can migrate this virtual machine. Remember that I used read-write mini storage specifically for that reason. So I can select the migrate option and it will go into a migrating status. So what we should see here in just a moment is it's going to switch over to worker 0 and be running on that particular node. Now in this instance, I only have 2 nodes. Oh, there it just did the switch over to worker 0. So I only have 2 nodes, so it doesn't really need to offer me a selection. It just moves it to the other one. The other thing that we'll note here, and I'll stop this ping now, so you see that there's a little bit of jitter inside of my ping times. Right, it went from below a millisecond for the most part up to 8 or 11 milliseconds at the top as it switched over from one host to the other. But otherwise, there was no downtime for my application, no lost pings, no lost connectivity, etc. It all stayed up exactly as you would expect. And my virtual machine is still running, just happens to be running from the other node. It doesn't know that it changed hosts because it's been abstracted away by OpenShift Virtualization. So the last thing that I'll do here is I will go ahead and stop my virtual machine. We can see that it goes through the standard process of shutting it down. If I go to my virtual machines overview here, we can see its current status. This will update in just a moment. There it goes to remove the node and IP address information. And I can also go here and I can delete my virtual machine. And when I do this, because I created using the URL type, so the data volume concept is responsible for the persistent volume, etc., it will also clean up all of those other objects associated with my virtual machine. So if I come down here to persistent volume claims, you can see that my PVC was removed, and thus so was my persistent volume. Okay, so that was a brief overview and introduction to OpenShift Virtualization and the capabilities associated with deploying and managing and consuming virtual machines through your OpenShift Kubernetes deployment. If you have any questions, if you have anything that we can help you with, please feel free to reach out to the BU and we will be more than happy to help with that. Thank you.